Okay, so let's do a review of integration for the final. Um, so, here's the main types of questions I'm going to ask you. There could be an indefinite integral, which is when it does not have the numbers on the top and the bottom. These numbers are called the limits of integration. And if you don't have limits of integration, like these are limits of integration, but if you don't have them like this one, then you call it an indefinite integral. If you do have them, then you call it a definite integral. An indefinite integral is the same as an antiderivative. It's the same as the stuff. Oops. It's the same as the stuff that we were talking about in 4.9. And then, so there's also U substitution, which is really, a U substitution kind of fits inside of indefinite integrals, and it also fits inside of definite integrals. So it's not exactly a separate thing, but I wanted to list it anyway because it's important. So anyway, let's talk about how to do them. So take a look at this one. We need to find the antiderivative of this. And this notation, this just tells you to find the antiderivative of the function inside. There's a table on page 358 of antiderivatives. There are certain antiderivatives that you should just know. You should just memorize them. Like powers of x, e to the x. Like as I look through this one, I see this is kind of a mess. I'll talk about this in just a second. This one is something that I know immediately. The antiderivative of e to the x is e to the x because I know my table. This one I recognize as well. If this 7 were a 1, this would be arctangent. The antiderivative of 1 over 1 plus x squared is arctangent. And I know that because I know my table. So with the 7 there, the antiderivative is going to be 7 arctangent. So just to summarize, this one's a mess, this one I'm comfortable with, and this one I'm comfortable with. So let's talk about this one. The truth is it's not that bad of a mess. I can divide through by this x. So x squared over x would just be x. Now, this is x to the 1/3. And if I'm dividing by x, what you do is you subtract the powers. So it's going to be x to the 1/3 minus 1. In other words, negative 2/3. That's this over this is x to the negative 2/3. Plus this, plus this. Like that. And now I'm comfortable with everything. These are just powers of x. This is like x to the 1, so its antiderivative is 1/2 x to the 2. This is a power of x as well, so if I add 1 to the power, I'm going to get positive 1/3. And then you're supposed to divide by that new power. Whoops. That looks a little goofy, but so it's 1 over 1/3 that I'm writing there. Once again, this is just going to look like it's staying the way it is because the antiderivative of e to the x is e to the x. And as we discussed, this one is 7 arctan. And since this is an indefinite integral, which is the same as an antiderivative, you want to put down the most general antiderivative when you do this. So on this step, the step where I found the antiderivative of everything, I want to write plus c. And yeah, there's not much to simplify, except I can't stand to see this 1 over 1/3. I consider that a fraction in a fraction, so I can't rest until I get rid of the fractions inside the fractions. but then we're good. All right. Next one. Next one is a definite integral, but we're going to start basically the same way as an indefinite integral. There's parts of this problem that are going to be the same as the last one. Specifically, the first thing I'm going to do is I'm going to find an antiderivative. So this one, there's not much for me to do here. There's no messes for me to clean up. So I can just go 1/2 x squared plus e to the x. Now, I'm not going to write plus c. When you're doing a definite integral, you just need any old antiderivative. You don't need the most general antiderivative. The most general antiderivative always has a plus c, but not putting that there just gives you some antiderivative, and then that's all we need here. What you do is you put this notation, it's like just a right bracket. There's no left bracket for this, but it's just a right bracket, and you write the limits of integration. Because what I'm about to do is I'm about to plug in this number and plug in this number and then subtract the two answers that I get. That's what this notation tells you to do. Let me use plenty of parentheses because this is the type of thing where if you don't use parentheses, you can get confused. But if I plug in 1, I get 1/2 plus e. And if I plug in 0, I get 0 plus, well, that would be 1. So this is 1/2 plus e minus 1. So e minus 1/2. So that's it. Okay. So then, right, let's talk about some more. So let's take a look at this one. This one, when I'm thinking of the formulas that are on my table, the table on page 358, I don't see anything like this. I also am not sure what kind of algebra I could do to make it look like any of the things on that table. I guess I could try to take this x inside the square root, but then I'm just going to have a square root and I would have like higher powers of x, and I don't see anything on the table that looks like that either. So that's not too promising. But, so here's the thing. In this class, we really only learn one trick that'll help you. If you're looking at something that's not on the table and you don't see any simple algebra that you can do to make it look like something that's on the table, there's only one trick that can help you, and that's U substitution. I'm going to introduce a new variable called U, and if I make a smart choice for U, this will work out. And typically, a smart choice of U is to let U be something that's inside of another function. For example, when I look at this, what jumps out at me is this x squared plus 1, because that's inside the square root. It's inside another function. And that's a smart choice for U. What we have to do to make a substitution is we have to talk about the differential du. And this works just like we did differentials before. This just means I do the derivative of this one, and I write dx there. And this is starting to fit together for me. So U substitutions are like a puzzle, and everything has to fit together. Of course, the thing under the square root is U, and this x dx is something that I kind of like because I see x dx here. So yeah, here's what I'm going to do. I'm going to say, off of this, I'm going to say 1/2 du equals x dx. Because I'm just kind of getting the part that I like by itself. I like the x dx. I didn't like the 2 so much. So, and what I'm going to do is I'm going to take the original integral and replace everything. Of course, what's underneath the square root is the easiest thing to replace, but also the x dx can get replaced with 1/2 du. And I like that because my goal is to write a new integral that doesn't have any x's in it, and I'm there. Okay, so I can pull the 1/2 outside. And of course, since I'm doing calculus, I prefer a 1/2 power instead of a square root. And so this is 1/2 times, and I'm adding 1 to the power, so 3/2, and then I would divide by 3/2, right? And at this step, since I just did the antiderivative, in other words, I don't have this symbol anymore. I don't have this s. Like, this is what's telling you to do the antiderivative, and then once I do the antiderivative, that's not there anymore. And simultaneously, this is the step where I should start writing plus c. Once you've done the antiderivative, c is part of the antiderivative because we're doing the most general antiderivative because this is an indefinite integral. Okay, so we're basically done. I just have to do a couple of things. Of course, I'm playing with my fractions here, but also when you do one of these, you don't want your final answer to be in terms of the variable that you made up. You want your final answer to be in terms of the original variable x. So while I'm playing with my fractions here, let me replace the letter u with what u was. U was this, x squared plus 1. And then this, the fraction comes out to 1/3. X squared plus 1 to the 3/2 plus c. Okay, so that's how you do a u substitution. Let's do another one. So I see this. This is significantly more complicated than anything you'll see on the table. Well, actually, some of the things on the table are complicated, but none of them look like this. So you're not going to find this one on the table, meaning that we have one hope to do this one, which is a u substitution. So what should u be? My advice for choosing u last time was to choose it to be the inside of some other function. And this is going to be, well, it's all kind of part of the same advice, but if you see fractions and you see a function that's on the bottom of a fraction, that's often a good choice for u. So let's try that. I'm going to have my du would be e to the x plus 4x dx. And I immediately like that. That's exactly what I see on the top. So actually, this one turns out to be easier than it looks. Of course, the bottom of the fraction is just u, and all of this stuff, including the dx, that's just du. So actually, let me write it this way. I'll just write a 1 on the top of the fraction and a du over to the side. Yeah. And now I have my integral that's just in terms of u, and now I think that this one is on the table. The antiderivative of 1 over x is natural log absolute value of x. Of course, we're doing u's, so this would be natural log absolute value of u. And I put plus c. And then finally, I want my final answer to be in terms of the original variable, so I'm going to replace u with this. Okay. Let's do another one. Right. So, okay. We see what we see. This is not on the table. So we are thinking about a u substitution. It worked out well last time, or a couple times ago, if I just let u be the inside of the square root. I mean, in general, I let u be the inside of some function, so, and the square root is a function, so why not? So let u be that. Du is just 3 dx. And okay, now, so remember when I told you that u substitutions are like a puzzle and everything has to fit together? Sometimes it doesn't immediately fit together, but with a little bit of work you can make it fit. Maybe the puzzle analogy isn't so perfect because you're not supposed to force a puzzle, and maybe I could say that we're not forcing this one. It's just a little bit of work to see how it fits. Anyway, what we're going to do is, let me put a little box around this. So I'm trying to transform this original integral into an integral that only involves u. But it's not always immediately clear how to do that, and sometimes you might want to start like sort of partially converting it, and you might have this awkward intermediate step where you have both x's and u's, and you're still trying to get rid of all the x's so that you have only u's, but it might not be clear how to do that all at once. So let me do the parts that I know. I'm not too sure what's going to happen with this x. I do know that this is the square root of u. And actually, if I think a little bit harder, I'll know what's going to happen with the dx, but let me not even worry about that now. I'll just write dx. So I didn't try too hard. I just replaced the really obvious thing. Of course, this thing is u because I made that u on purpose. And that's the only thing that I replaced. I still have to replace this and this. What you have to do is solve equations sometimes. So what am I going to replace x with? I'm going to take this and I'm going to solve it for x, and that's what I'm going to replace x with. What am I going to replace dx with? I'm going to take that and I'm going to solve it for dx, and that's what I'm going to replace dx with. So here I go. This one tells me u minus 7 equals 3x. U minus 7 over 3 equals x. This one tells me 1/3 du equals dx. So now I can replace everything. X gets replaced with this. Dx gets replaced with this. And now I have an integral with all u's and no x's. Okay, great. So how do I do it? Well, first of all, this 3 in the bottom and this 3 in the bottom, so those would multiply and make like 1/9, and I can take that 1/9 on the outside. And then I would only have u minus 7 times the square root of u. And now, this is still not something that would be on the table exactly, but I can easily make it that way. If I multiply the square root of u through, like this square root of u is like u to the 1/2. So u to the 1/2 times u would be u to the 3/2. U to the 1/2 times this would be 7u to the 1/2. And then I'm just going to have some powers of u, and I know how to do antiderivatives of powers of u. So that's the plan. So this is u to the 3/2 minus 7u to the 1/2. Like that. And that turns into, here I'm going to use brackets so I don't forget to distribute the 1/9. But so this will turn into u to the 5/2 because I add 1 to the power. And then I would have to divide by 5/2. In other words, what goes here is 2/5. I'm dividing by 5/2, right? Minus 7 times, this is going to turn into u to the 3/2, and then I would have to divide by 3/2, so what goes here is 2/3. And then I'll just remember to put plus c at the very end. And yeah, so sorry, I didn't plan this out too well, but let me just write the answer sideways here, because just a couple of things I have to do. I want to distribute the 1/9 through. I also have to leave my final answer in terms of x's and not u's. So here we go. This fraction is now going to be 2/45, right? So I'm going to have a 2/45 u to the 5/2. So that's 3x plus 7 to the 5/2. Okay, and then I'm going to have a 9th times 7 times 2/3. So 7 times 2 is 14. 9 times 3 is 27. So 14/27 u to the 3/2. So that's 3x plus 7 to the 3/2 plus c. So that's my final answer, and sorry for having to write it sideways. Okay. So yeah, that one is a harder one. The ones where you have to really work to make the puzzle fit together are a bit harder. So yeah. Let's do, because the last several were indefinite integrals, if you noticed, the last several examples that I did. Let's do another definite integral, so it has the limits of integration. This one's going to be another u substitution, but it's not going to be hard like the last one. I can tell you, and if you get good at this, you can really look one step ahead as you do u substitutions. I can tell you what's going to happen here. I'm going to let u be the inside of this. Du is going to be 2x dx. The x dx is something that I see right here, and the 2 is just a constant. That's something that can be fixed, and that's going to be that. So u equals x squared. Du equals 2x dx. x dx is right here, so I like that. So let me write 1/2 du equals x dx. That's what I mean when I say fixing the 2. You can just move the 2 over. And what do we do? So the x dx is 1/2 du. This cosine of x squared is cosine of u. And so this is it. I have my integral in terms of u's instead of x's. And now I'm going to do the thing with these numbers. These numbers, when you make a substitution, these numbers change. You plug these numbers in for x, because basically these are limits for x values. These should be considered as x values, and what we want to put here is the corresponding u values, which we get by plugging these in for x to see what u is. In other words, what goes down here is 0 squared, which also happens to be 0. But what goes up here is the square root of pi squared. In other words, it's now just pi. Great. Okay, so then I can pull the 1/2 out. Antiderivative of cosine u is on the table. Antiderivative of cosine is sine. Because I did this, because I changed my limits, these limits go in directly for u. I don't have to go back. I don't have to replace u with x squared again. I just put these numbers in directly for u. You plug in this one and you plug in that one and you subtract them. Oops, I wrote theta instead of 0. But actually, sine of pi is 0. Sine of 0 is 0. So this is all just 0. One more for this. It's another definite integral. And this one has a fraction in it. It's not a terribly complicated fraction, but you know, it's again, if you look for something like this on the table, you're not going to find something quite like this. So we have to use a u substitution. I don't see any square roots or other functions with something on the inside, so I'm going to use some advice from a minute ago and let u be the bottom of the fraction. du would be 2 dx. And, right, so let's go in here and start trying to replace things. So, of course, the most obvious thing is that the bottom of the fraction is now u. Let's talk about the top of the fraction. The top of the fraction was supposed to be x, and I'm not sure what to replace that with. However, in the past, what has worked for us is looking at the substitution we made, solving it for x, and then using that. So that's what we're going to do. U minus 1 equals 2x, u minus 1 over 2 equals x. So I replaced x with u minus 1 over 2. I need to replace dx with something. I'm not sure what to do. In the past, though, what has worked is just taking this and solving it for dx. So 1/2 du equals dx. Okay, So I'm pretty happy with that because I don't have any x's left or a dx. It's only u's. But before I forget, I should change the limits. So these numbers should be the u values that correspond to these x values. So corresponding to this x value, if I plug it in, I get u equals 1. And corresponding to, if x equals 1, u would be 3. So there we are. Okay. Now let's see if this new integral is something that's any better. Yeah, so this is a fraction in a fraction. So here's how I'll take care of it. I guess what I'm doing is, like, the bottom is like u over 1, so I flipped the bottom and I multiplied like that. And yeah, so I see these 2's in the denominator, and these 2's are just constants, and that can get pulled all the way out. So I can write 1/4. And then what do I have? I just have the u minus 1 on the top and the u on the bottom. Yeah? And this is not something that you'll find on the table. If you look for something like this, it's not on the table. But there's a simple algebra thing I can do, which is just dividing through by the u that's in the bottom. Because if I do that, u over u is 1. 1 over u is 1 over u. And these are things that are in the table. So I'm going to use like a left bracket and a right bracket just so I remember to distribute the 1/4. But the antiderivative of 1 would just be u. The antiderivative of 1 over u is natural log absolute value of u. And then I'm going to plug in 1 and plug in 3. So this is 1/4 3 minus ln 3 minus 1/4 1 minus ln 1. Natural log of 1 is 0. And here, so I would have a 3/4 minus 1/4. So that's going to be 1/2 minus ln 3 over 4 from this. And that's it.